Okay, let me recall what we are doing. So we have a function g from the complex numbers to the real numbers that was continuous, invariant under complex conjugation, and that satisfies some asymptotics when z goes to infinity. It goes like the logarithm of the absolute value of z. Then with this function g, we define a height. If alpha is an element of Q bar, then the height corresponding to g of this number alpha was defined as 1 over d, then the logarithm of AD, and then plus the sum for all beta inside the Galois orbit of alpha of the function g evaluated at beta. Okay. Remember that to the polynomial alpha, we associate the minimal polynomial of alpha that has the shape AD x to the d plus A0. And then here we see the leading coefficient of the minimal polynomial and the degree of the minimal polynomial. If alpha is an algebraic integer instead of being just an algebraic number, then we know that the minimal polynomial will be monic. So AD will be 1, log of 1 will be 0, and then we get that the height g of this algebraic integer will be just the average value of the function g at the conjugates of alpha. Then we define the essential minimum of the height function is just the lim inf of h of alpha for alpha inside Q bar, and then the essential minimum, but the integral one of hg will be the same, the lim inf of h alpha, hg alpha, but now alpha will run only on algebraic integers. And then, of course, we have an inequality like this because here we have just more points. Since we have more points, then we can maybe go below this element here. Okay. Now, the last day, we discuss lower bounds because we want to estimate this quantity. And to estimate this quantity, what we can do is to start with lower bounds and to upper bounds and try to see if between the upper and lower bounds we can close the gap and get a nice understanding of this value. And we started looking for upper bounds, and we did a little bit of potential theory and remember what is the capacity of a set and the equilibrium measure. So we have K inside C, a compact set of capacity 1. Then there is a unique measure, mu K, which is called the equilibrium measure of K. For instance, the basic example of a set of capacity 1 will be the unique disk. And then the equilibrium measure, mu K, will be just the hard measure on the unit circle. Remember when we studied this capacity theory that without the equilibrium measure as the distribution of charges in the space, we have the charges, in this case, inside the unit disk, and then the fact that the equilibrium measure is the hard measure means that all these charges will go to the boundary of the disk, just to the circle, and they will be equidistributed along the circle. This is why we get the hard measure of the unit circle. And then we discussed two theorems, one by Fequete-Sego, that tells me that if I have a set of capacity bigger or equal than 1, then I can find a lot of algebraic integers that are close to this set. And then another theorem by Rumely that tells me that if I start taking algebraic integers that were approaching this set, they are closer and closer to this set, then the limit will be exactly this equilibrium measure. So there is a relationship, very nice relationship between physics and arithmetics in the sense that, in some sense, the algebraic integers know a little bit about forces and repulsory forces. But the consequence of this is the following proposition. If I now look at the integral of the function g d mu k, here I have to assume that k inside C is compact and invariant under complex conjugation. Then I can, and capacity of k exactly equals to 1 to apply Rummel's theorem. Then if I look at the integral of g d mu k, this will always be bigger or equal than the essential minimum, but the integral one. And of course, we know that this is bigger or equal than the usual essential minimum. Okay. Why this is so? Proof. Well, we know since K is a compact set, which is invariant in the complex conjugation and has capacity K equal to 1, using Fekete-Sego and Rumely, so Fekete-Sego plus Rumely, implies that there exists a sequence alpha n belonging to the algebraic integers such that the whole orbit of alpha n is contained in the neighborhood of radius 1 over n of k, and alpha n is different from alpha m whenever n is different from m, or maybe the orbits are different to make it generic. So we can construct this sequence applying Rumely and Fekete-Sego, because Fekete-Sego tells me that every time I have a small neighborhood around k, I can find an infinite number of algebraic integrals contained there. So I can take one that is different of the previous one. And we also know that by Rumely that the counting measure delta of O of alpha n converges to the measure mu k. This was the statement by Rumely. But the interesting thing now is that in principle, we can think that this convergence is only weak convergence, but all the orbits are containing a fixed compact set. Because the moment I start with k equal k is compact, then I start, for instance, with the ball of radius 1 around k. This is still compact, and everybody is containing this compact set. So this convergence is not just weak convergence, but it's proper convergence. Okay. And proper convergence means that I get continuity with respect to integrals of any continuous function. So I don't need to ask my function to be constant. Now, what is then the height of alpha n? The height of alpha n, since the alpha n are algebraic integers, this will be equal to 1 over the n, the degree of alpha n, and then the sum for all beta inside the orbit of alpha n of the function g evaluated at beta. But now we see that this is nothing else than the integral of g with respect to the counting measure of alpha n. This was the definition of the counting measure of alpha n. And this converges to the integral of g d mu k, because g is continuous on the whole C. I don't care that the limit at infinity is not bounded, because I have proper convergence of measures. Since I have proper convergence of measures, I know that this integral converges to this integral. Okay? So I have a sequence of integers whose limit height is this quantity. But this is exactly telling me that so this automatically implies that the integral of g d mu k has to be bigger or equal than the essential minimum on the integrals of Hg. Because this is the minimal possible limit point. This is a limit point, so it's bigger. Okay? So we have a very nice upper bound for the essential minimum, just integrity. Now one can ask, in the same way that we had when we were discussing lower bounds, we have this very nice theorem by Vallée that was telling you that, in fact, the family of lower bounds we obtained was sharp. Now we can ask, is this family of upper bounds sharp? So if I now take all possible compact sets of capacity 1, and then I take the infimum value of this integral, do I get exactly the essential minimum? And then we will be in good shape because we can close the gap. Unfortunately, it's not true. So one can show that this family of upper bounds is not sharp, and we need a better upper bounds. And these upper bounds, luckily, a few years ago, well, last year, to be more precise, a couple of papers appeared from Smith and Orlovsky-Zardari that can be thought as a very flexible Fekete-Szego theorem. In the sense that if you look at Fekete-Szego theorem is telling you that if you have a set which is big enough, then you can find a lot of algebraic integers in this set. And Rumeli is telling you that if your set is of capacity 1 and you get points which are very close, then you can get the equilibrium measure as a limit of algebraic integers. But then one can ask, okay, but what are the measures that can be written as a limit of orbits of algebraic integers? Are just the equilibrium measures of sets of capacity 1? Is the convex closure inside all the measures of the sets of capacity 1, or what kind of measures can be described as what are the limit measures of algebraic integers? And then we have the following theorem by Smith and Orlovsky-Zardari. That tells us the following thing. So if I have mu, a measure on C with compact support, and invariant under complex conjugation, a probability measure, total mass 1. So a probability measure on C with compact support, invariant under complex conjugation. Then the following are equivalent. The first condition is that for every polynomial Q inside set of X, so for every polynomial with integral coefficients, the integral of log of absolute value of Q d mu has to be positive. So I need a measure such that the integral of log Q has to be positive for all possible polynomials with integral coefficients. Okay? And the second condition is that there exists a sequence of algebraic integers alpha n inside this set part, such that the orbit, the counting measure of alpha n, so the counting measure of the Galois orbit of the algebraic integers, converge to this measure mu properly. So that if we can determine all measures that are limit of algebraic integers just by testing this condition. So in some sense, these are very good news because now we know all possible measures that are limit of algebraic integers. The bad news is that this is an infinite number of conditions. So in the previous case, we only need to check that we have a set of capacity 1, which is more or less possible to check. Here we have to check that a lot of integrals are positive. So we get a very nice criterion, but a little bit difficult to manage. There is also another thing to say here is that I am just looking at probability measures with compact support. Then, but it is not difficult, in fact, with my collaborators, so corollary, myself and Bincancu, Ricardo Menares, and Sombra. What we did is the following thing. So the point is that typically we're interested in measures that does not necessarily satisfy the bang of compact support. For instance, you can imagine inside P1, you have the Fubini's 2D metric, and if we restrict this to the complex numbers, this will not be of compact support. So we need to extend this result to measures that are not with compact support, but we need to be able to control the height. So we cannot go to weak convergence, we need at least logarithmic convergence. And then the corollary is that now if mu is a probability measure that belongs to P log of C, remember that these were the probability measures such that the integral of log plus was finite. So mu is a measure in P log C, invariant under complex conjugation. We don't need compact support, can be any measure, then the following are equivalent. Then the first condition is exactly the same, that for all Q in set of X, the integral of log absolute value of Q d mu is bigger than 0. But now the consequence, since now my measure does not have compact support, I cannot have proper convergence, because in order to have proper convergence, remember that I need that everything is inside the same compact support. The conclusion is that there is a sequence. There exists a sequence of algebraic integers alpha n inside set bar, such that, and the same thing, the counting measure delta of alpha n converges to mu, but now logarithmically. So it's stronger that we converge, so it converges logarithmically, which means that I can integrate with respect to functions that growth at most like a logarithm. Okay. Now the corollary of this result is that if mu belongs to P log of C and invariant under complex conjugation, and the integral of log of absolute value of Q d mu is bigger or equal than 0 for all Q inside set of X. So if I have a measure that satisfies this first condition, then the integral of G d mu will be again bigger or equal than the essential minimum, but for integers of AG, and this will be bigger or equal than the essential minimum of AG. Okay. And now the proof is almost the same, because if I have this condition, then this theorem tells me that I have a sequence of algebraic integers. So there exists a sequence of algebraic integers such that the counting measure delta of O alpha n converges to mu. Now the height of alpha n is equal to, as we have done before, the integral of G d of delta O of alpha n. Again, I am using that alpha n is an algebraic integer. And we know that this converges to the integral of G d mu k, d mu. Because the important thing here is that this convergence is logarithmic, and this function is bounded by 2 times the log of z, for instance. So we get this convergence, and so this value is a limit value of the heights of a sequence of integers. Hence, it is bigger or equal than the essential minimum the integral essential minimum, which is bigger or equal than the essential minimum of AG. It's clear? So now we have these two, these upper bounds, which are much more flexible. In fact, one can see that this theorem is much stronger than Fekete-Sego plus Rumeli, because if I have a set of capacity 1 and I have the equilibrium measure of a set of capacity 1, of course I can say, since I know by Fekete-Sego and Rumeli that I have a sequence that converges to this guy properly, then I have this condition. But the point is that this condition is very easy to satisfy or to verify in this particular case. So for instance, whenever you have a measure whose potential is positive, then you will get 1 almost for free, and then you will get 2. But there are measures that satisfies 1 that do not have a positive potential. Questions here? There is one interesting thing to notice, is that the upper bounds we see before, that if you take a set of capacity 1, this gives me an upper bound. Now, these kind of upper bounds are invariant under translation by reals, in the sense that if I have a set of capacity 1 and I translate it, it still will have capacity 1. If it was invariant under complex conjugation and I translate it by a real number, it will still be invariant under complex conjugation. But this condition is not. I mean, this condition that, because here I have to test for all integral polynomials, and this condition is not invariant under translation by reals, okay? Which is in some sense a good thing, because let's say the distribution of integers is not invariant under translation by arbitrary real numbers. Okay. Good. Questions so far? Okay, so now we have so in conclusion, I can look at the supremum for all polynomials Q inside set of X and R bigger than 0 of the infimum over set inside C of G of set minus R log of absolute value of Q. This was the lower bound we discussed the previous day. This is smaller or equal than the essential minimum of AG. This is smaller or equal than the essential minimum with integer numbers of AG. And now this is smaller or equal than the infimum for all of the set integral of G d mu for all mu inside P log of C, such that the integral of log P, log absolute value of P d mu, is bigger or equal than 0 for all P inside a set of X. Okay, so this is what we have up to now. We have a lower bound, which is smaller than the essential minimum. This is smaller than the essential minimum with integral points. And this is smaller or equal than the infimum of all these integrals, but only restricted to these measures, the measures that satisfies this Smith condition. Okay. And now, in some sense, what we would like, or the dream will be that this quantity and this quantity are the same. Because if we know that this quantity and this quantity is the same, then the sandwich closes. We get that in order to compute the essential minimum, we only need algebraic integers. We don't need arbitrary algebraic numbers. And we get a perfect sandwich that tells me to approach this value as much as we want, if we have enough computational power. Okay, and now what is the run we can try to find a result that tells me that optimization, like supremum of something, agrees with another optimization, like the infimum of something. Well, this now, let's go to applied mathematics, and let's go to linear programming. Linear programming is just the problem of optimizing a linear function restricted to a set of semilinear restrictions. A very simple problem. apparently. So linear programming. Let me write down a very abstract version of linear programming because we will need this version in our setting. So what is linear programming? I need two vector spaces, E and F vector spaces. And I have a bilinear map, A from E cross F to R. Let's say that they are R vector spaces. And I have a bilinear map. Of course, whenever I have a bilinear map, I can think that I have a map that I will still call A from E to F dual, and a map A transpose that goes from F to E dual. Okay, the bilinear map can be seen as a map like this. Now, so this is the first ingredient, two vector spaces that are related by a bilinear form. The second ingredient I need are linear maps. I have U an element of E dual seen as a linear map on E, and B an element of F dual seen as a linear function on F. And then the third condition will be the restrictions, and the restrictions should have the shape of a convex cone. So I have sigma inside E and tau inside F, convex cones. Okay. Now, whenever I have a convex cone in a space, remember that there is the definition of the dual cone. So the sigma dual will be just the elements U or X inside E dual, such that, or maybe, what letter should I be? No, B I have used it. So W inside E dual such that W times X is bigger than 0 for all X inside sigma. Okay, whenever you have a cone in a space, you can look at the dual cone in the dual space just by asking that the values on every point in the cone has to be positive. Okay? And now, with all these ingredients, I can ask for a optimization problem. So my optimization problem will be P is to find the supremum of U of X. So I am just looking at the maximum or the supremum of a linear function, sup of U of X, with the restrictions that X has to be in sigma, and that if I look at, or maybe right like this, B minus A of X has to belong to tau dual. Okay, you see that it's just, I am looking at the optimization of a linear function with semi-linear restrictions that X has to be in a given cone, and then the other restriction has to do with the other space. So I want that when I send X to the other space by A, or to the dual of the other space by A, and add B as a vertex, it belongs to the dual of the cone tau. Okay? Most of the usual problems in optimization can be written in this abstract way. Now I will use the letter P to denote both this value, if exists, and this problem. So P will be the problem of finding P, let's say, by abuse of notation. Okay. Now, what can we do with this problem? Well, whenever you have a problem that asks you to optimize a function with some restrictions, then you use the Legendre formalism and put some multipliers. Now I want to divide the restrictions into two sets. One is just being in this cone that I will leave as it is, and the one that I will use the multipliers will be for the other condition, because this is the condition that goes to the other space. So let me define now P prime to be the following problem: the supremum for all X inside sigma. And now I add a variable for each restriction. But observe that since my restrictions are that B minus AX belongs to tau dual, the easy way to get multipliers for these restrictions is to take elements in tau. So this will be the infimum now of Y inside tau of the function U of X, but I have to add the multipliers, plus B of Y minus A of x, y. Okay, so I can look at this new problem. Here I have just added this condition multiplied by y. If I multiply by y this condition, I get b of y minus a of xy. And we can see that these two problems are the same. Okay. Why so? Because here I am just taking the supremum for all x in sigma, and then the infimum for all y in tau. Here I was taking the supremum for all x in sigma. That satisfies this condition and a different function. So in principle, they look a little bit unrelated. But if you look closely, if I start with a point x in sigma, if x is in sigma, but b minus ax is not in tau dual, this means that there exists a y inside tau such that b of y minus a of xy is negative. But tau is a cone, so I can make y as big as possible. So I can make this go to minus infinity. Since this can go to minus infinity, when I take the infimum for all y in tau of this quantity, this is minus infinity. But minus infinity is the neutral element of the Parisian soup. Hence, it's like it is not there. But if x belongs to sigma and b minus a of x belongs to tau dual, then for all y, b of y minus a of xy will be bigger or equal than 0. Since here I am taking the infimum, and the only part that depends on y is this part here, and it is positive, the infimum will be achieved when this quantity is 0. And this is achieved as 0 at y equal to 0. But if I put y equal to 0, I get exactly the original problem. So you see that these two problems are exactly the same. So we get that using Lagrange multipliers, we get this new problem. Now, we have converted my problem of the soup with these two conditions as a problem that has a soup and an inf. And then why not? I can switch the soup and the inf. Why not? I can define the dual problem just switching the soup and the inf. D will be taking the inf for all y inside tau of the soup for all x inside sigma of the same problem. U of x plus b of y minus a of xy. Okay. And now I can play exactly the same game I made before, but in the inverse direction. And I can see that this problem is equivalent to looking at the infimum, but now of the function b of y. And now the conditions are that y belongs to tau, and that A transpose of y minus u is now the guy that has to live in B dual. So there is a change of sign because on one hand I have a supremum, the infimum, and now is the other way around. Okay? So you see, it's some kind of a dual problem. No? The role of u here and b here are switched. Now I have the b as my linear function and the u as the vertex of this cone. Okay? And of course, we have a weak duality that tells me that whenever I have the soup of the inf and I switch, of course, the p has to be smaller or equal than d. Okay? So if I take the supremum of all possible infimums, or I take the infimum of all possible supremums, it's bigger to get the. Okay. So for the moment, I have done absolutely nothing. I mean, that looks like, okay, yeah, of course, you get something which is bigger. But as we will see, we get much more. Okay, now I have a little bit of terminology, because you see this problem can be out of control. For instance, it might happen that there is no x that is in sigma and that satisfies this condition. And then the supremum, since this is the empty set, the supremum will be minus infinity. Or it might happen that I have so many guys satisfying these two conditions that this is infinite. Okay, so then I will say that P is feasible if there exists an X inside sigma such that B minus A of X is in tau, which is equivalent to asking that P is strictly bigger than minus infinity. And we'll say that P is bounded if P is smaller than P. Okay? And similar for D. So we'll say that D is feasible if there exists a Y inside tau such that AY minus U belongs to sigma dual, which implies now that D is smaller than plus infinity, and we'll say that D is bounded if D now is smaller than minus infinity, okay, because we are looking at that. And of course, if, since we have this weak duality, if D is feasible, then we have an upper bound of P. So D P feasible implies that P or D is bounded. It's clear, no? So if D is feasible, this gives me an upper bound of P. If P is feasible, this gives me a lower bound of D. Okay. But if one is bounded, I don't know anything about the other one. So I only have the implication in this direction because I only have this inequality. And now we can write the classical theorem of linear optimization. It's the following: if E and F are finite dimensional, and sigma and tau are closed cones, okay, then the following are equivalent. One, P is feasible and bounded. And the second one is that D is feasible and bounded. And in this case, strong duality holds. In the sense that P is equal to D. So it's not just that one is smaller than the other, but they are exactly the same. So the two optimization problems gives exactly the same result. But of course, this is a much more restricted setting. So in my original setting, E and B were two vector spaces, arbitrary, any dimension, infinite, no, finite, whatever. Sigma and tau were cones, open cones, closed cones. The only condition that they were convex cones. But if I know that my spaces are finite dimensional and the cones are closed cones, then one problem is feasible and bounded, the other one is feasible and bounded, and in this case, the two problems have exactly the same solution. Okay. Maybe I can give a short proof of the result. At least during the course, you'll get a proof. Now, the idea is to start with, so we will assume that P is feasible and bounded. Now we need to show that D is also feasible and bounded, and that then the two guys are the same. By instance symmetry, the other equivalents will follow the same pattern. Now we already know that D is bounded. So this is the easy part. Since P is feasible, then D is bounded. And now I want to look at two spaces. So in R times F dual, I look at the following spaces. So B will be just the set of all elements of the shape U of X. Remember that U of X is our target function that we want to optimize. And then A of X for all X belonging to the cone sigma. So I am taking a space that gives me the target function and then gives me the shape of the image A of X for all X in sigma. And for every lambda in R, I will define the set W lambda, also inside R times F dual, as the set of elements T, comma W, satisfying that T is bigger or equal than lambda, just this condition here, and that B minus W belongs to tau dual. Okay, so I am taking this condition. Now one can make a picture here. So let's say that this is R, and this direction is F dual. Then this first space is a cone, because remember that sigma is a cone. This is a linear map. This is a linear map. So B will be something like this. So this is my space B, a cone. B lambda, observe that this looks very much like the condition in my optimization problem. That, oh, it's not here, the P problem is only the D. But remember that the condition was that X belongs to sigma, and that B minus A of X belongs to tau bar. Okay, so elements that are in the intersection of these two sets will be exactly elements that are feasible for the problem P. Okay? But we see, so I have some condition on W on F dual, but the condition on T is just this thing here. So my W will be something like this, a cone in F, and then I will move on this direction here. So I can move here in this direction and this direction. Okay, so when I change lambda, the only thing that happens is that these guys will move. Now, if I look at yeah. Yes. Now, since P is feasible, we know that there exists a sigma, an X, that is in sigma and such that B minus A of X is in tau dual. Okay? But then this means that if I look at the point U of X and A of X, which is an element in B, but I take now lambda to be any number which is smaller or equal than U of X, then this will also belong to W lambda. Because A of X, by this condition, satisfies this condition here, and since I am choosing lambda to be smaller than U of X, the first variable also satisfies this condition. So we see that there exists a lambda, so B intersected W lambda is known. So in this picture, this means that if I move this W lambda that can be moved in this direction, I move it to the left, at some point I will encounter B. On the other hand, I know that P is bounded. Since P is bounded, this means that if I took now lambda prime, which is bigger than P, then one can see that B intersected with W lambda prime, this has to be the empty set. There is no way that I have an element, because if I had an element that belongs to the intersection, the value U of X will be smaller or equal than P, but I am taking lambda to be bigger than P. So this is empty set, which means that in this picture, when I move W to the right, they has to be separated. And of course, there will be a point, lambda 0, which is the boundary point where they meet. So let's take let's take this limit point. So we take lambda 0 to be the sum of all the lambdas such that B intersected W lambda is non-empty, which is the same as the infimum of all the lambdas such that B intersected with W lambda is empty. Okay, and this is the limit point. Now let's take some epsilon strictly bigger than 0. We know that B intersected with W lambda 0 minus epsilon. This has to be non-empty because of the condition of lambda 0. But then the fact that this guy is not empty is telling me exactly that I have an element on the feasible set whose value is bigger or equal than lambda minus epsilon. So this implies that lambda 0 minus epsilon is more or equal than the problem P. And since epsilon is arbitrary, this implies that lambda 0 has to be more or equal than P. Okay. Now let's look at B intersecting with W lambda 0 plus epsilon. Now this guy is the empty set. And now we play the usual game in convex analysis. Whenever you have two convex sets whose intersection is empty, you look for an hyperplane that separates them. No, this is known in this literature, is known as the Farkas lemma, but there are many variants of this separating hyperplane. And the precise version that I want to use is the following. Since B is a cone starting on 0, and W lambda is an affine set, and they don't touch, then what one can prove is that there exists an H and hyperplane, a linear one, so H will be of the shape, yeah. So how I am taking the H, yeah. B comma Y in coordinates, such that H restricted to B is bigger or equal than 0, and H restricted to W lambda is strictly smaller than 0. One can find a hyperplane that separates these two guys, but in a very strong sense. In the sense not that it is bigger or equal than 0 in one side and smaller or equal than 0 in the other, but truly it is bigger or equal than 0 in one side and is strictly smaller than 0 in the other, and it is just a linear condition. Okay. In the notes that you can find in the web, there is a precise reference or where you can find this strong situation. Okay, and now I write my hyperplane as a condition like this. So H of U W, for instance, will be of the form B times U plus W evaluated at Y. Now, since we are in a finite dimensional space, this Y, I can think it as an element of F. Because now, since we're in finite dimensional spaces, the dual of a space is the original space. This is something that I cannot do in infinite dimensional spaces. Now, what are the conditions, these two conditions? Maybe we can write this down. So these two conditions tell me the following, that if I look at Bu of x plus A of xy, this has to y, this has to be bigger than 0 for all x inside sigma. The condition that H restricted to B has to be bigger or equal than 0, and the shape of B translates into this condition. And the other condition is that Bt plus B of y minus B prime of y has to be strictly smaller than 0 for all B prime inside T tau dual. Okay. So the condition that the restriction to W dual has to be strictly smaller than 0 translates into this condition. Now, what we can see is that if we take B prime in this condition to be just B minus A of B, A of x inside tau bar, tau dual for X inside sigma. So this guy exists because the problem P was assumed to be feasible. Then we apply this condition for sigma. This quantity for X is bigger than 0. This quantity is strictly smaller than 0, which means that this quantity has to be strictly bigger than this quantity here. And what we get is that BUX plus A of XY has to be strictly bigger than BT plus B of Y minus B prime of Y, which by this condition that B prime is this guy here, the B is cancelled, this is BT plus A of XY. Okay? So we have that this quantity has to be strictly bigger than this quantity here. Okay? But this for all T smaller or equal than lambda. Since this has to be true for all T smaller or equal than lambda, for all T bigger or equal than lambda, we deduce that B has to be strictly negative. Okay? So because B times this quantity has to be strictly smaller than B times T, and T can be arbitrarily big and positive. Since T can be arbitrarily big and positive, B has to be negative. And since the inequality is strict, has to be strictly negative. Since this is an hyperplane, I can rescale and I can assume that B is equal to -1. So my hyperplane H now is of the shape -1y. And then the condition is that minus T plus B of Y minus B prime of Y has to be strictly smaller than 0 for all B prime inside tau bar and T bigger than lambda. And observe that this condition automatically implies that Y has to belong to tau. Because if this has to be negative for all B prime in tau dual, and Y is not in tau, then I will find a B prime in tau dual such that B times Y is positive, and then I will make this condition not to be satisfied. Okay? And then the condition that minus U of X plus A of XY, which is the other condition, has to be bigger or equal than 0, implies that A transpose of Y minus U has to belong to sigma dual. Which means that Y is in the feasibility set of D. So we get that this is feasible. I need 1 more minute to finish the proof. Okay. So which means that D is feasible. And since D is feasible, we get the equivalent. So we started with P bounded and feasible, and we conclude that now D is also bounded and feasible. But not only we get this, because if I now take B prime equal to 0 in the condition, and I take T to be equal to lambda 0 plus epsilon, and then I get the Y, use the Y is feasible, we obtain that B of Y has to be smaller than lambda 0 plus epsilon. But remember, Y is in the feasibility set of D. And I have this bound. This implies that D is smaller than lambda 0 plus epsilon. And since epsilon was arbitrary, this implies that D is smaller or equal than lambda 0. But remember that we already said that lambda 0 was smaller or equal than P. And we have weak duality, which tells me that P is smaller or equal than D. So we get a nice sandwich, and we get that D and P are the same. Okay, so even if in general switching the max and the min gives a smaller thing, in this concrete case, we get exactly the same value. Questions so far? Okay, so then for the next day, what we will show is that my problem of finding the essential minimum can be put in this scheme, but now it will be an infinite dimensional scheme. Then I will claim that we can prove a strong duality. I will not do here, but you can look at the papers, and then we'll extract some consequences and try to find nice bounds of the essential minimum in some concrete cases. Thank you.
Thank you, Ignacio, for your talk. Are there questions, comments? Questions? I don't have questions. So let's thank the speaker.